Day one and all, welcome back to the HESA e-library, also called the HESA Video Bank. This part of the series would be part 2 of the inorganic chemistry discussion. And then we'll talk about quantum numbers, everything about quantum numbers. Now, quantum numbers were briefly explained at the latter part of the part 1, but let me recap on what we said. We said that in order to describe the nature of the orbital and the nature of electrons, we have some numbers and symbols that we use, numbers, letters, and symbols that we use. And these numbers, letters, and symbols are called quantum numbers. Now, these form the basis of quantum physics, right? Good. Now, there are 4 quantum numbers that we have to talk about. First one is principal quantum number. Right now, the principal quantum number is denoted by the value n, right? Small n. Now, it is called the energy level, known as the energy level, or the shell, the main shell. I'll be using these terms interchangeably. So the energy level or the shell, right? Now, the shell takes names from letters. So you start from K. K is the closest shell to the nucleus. Then we have L. Then we have M. N. It follows like that, right? So that is what we have. Now, the shells will tell you how close you are to the nucleus. So just for us to understand, if the nucleus is like this, right? The first shell will be here. That is the K shell. Then the next one will be here. That will be the L shell. The next one will be here. That will be the M shell. Then I can draw another one for the N shell. So you realize that as we go forward, right? As we move, the K is number 1. The L is number 2, the N is equal to 3, right? And so you realize that as the numbers increase, the electrons are further away from the nucleus. And so it shows, right? The principal quantum number shows us how close you are to the nucleus. That's not the only thing. It's also called energy level because the principal quantum number tells us the energy of the electrons. And so technically, if you are in, let's say, shell 3, the assumption is that you have higher energy level than the one which is in shell 1. The ones closest to the nucleus, right, are more stable than the ones far away. Because the ones closer to the nucleus are more stabilized by the nucleus. So that's the idea, right? So something about principal quantum number, also called the shell, it's denoted by N. It shows the energy of electrons, and then it shows how close the electrons are to the nucleus. It takes letters from L, M, N, right, up to Q, right? Yes, and then if we want to find the maximum number of orbitals, electrons that can enter the shell, we use this formula, 2n squared. So if n is equal to 1, then we have 2 to bracket 1 squared. 1 squared is 1 times 2 is 2. So the K shell takes only 2 electrons. The next one, we have 2 into bracket 2 raised to the power 2. 2 raised to the power 2 is 4. 4 times 2 is 8. So you realize that the L shell will take 8 electrons. Now, when n is equal to 3, that is, n is equal to 3 will be the M shell, right? Then we have 2 into bracket 3 squared. And then 3 squared is 9. 9 times 2 is 18. So this is 18, right? So that is that for, that's very simple. Very simple. It goes like that, right? So that's everything about principal quantum number. Now we build on. The next type of quantum number we have to consider is the azimuthal quantum number or orbital quantum number, right? Yes, it has other names. It has other names like angular momentum quantum number, right? Or subsidiary quantum number. So it has a lot of names, right? And all these names can be used. Now, we are saying that it tells us the shape of the orbital. It tells us the shape of the orbital. So that is one of them, right? It tells us the shape of the orbitals. Now it takes value from 0 to n minus 1. So if we are talking about the first shell, which is n is equal to 1, the K shell. Now n minus 1 will be 1 minus 1. N minus 1 will be 1 minus 1, which will be 0. So the only value of L, which is the azimuthal quantum number we can get, is 0. That is all, right? Yes. Now they are telling us that it tells us the shape of the cell. So how can this tell us the shape of the cell? Now for each value of L, there's a particular shape we are looking at. So if L is equal to 0, right, Now, the shape we are looking at, the symbol that is used to represent that is S. If L is equal to 1, then we have P. If L is equal to 2, then we have D. If L is equal to 3, we have F, right? Good. Now, this S is known to be spherical. So that's the shape we are talking about, spherical. Now, P is known to be dumbbell. So it's known to be dumbbell shape, right? Now, the D is quite complex, the D and F. The D has some clove-like properties, but then all of them are complex. So usually we limit ourselves to the first two, right? Per our discussion, that's as far as we go. As far as we go, per our discussion. Good. So let's go back to our conversation. Good. Let's take it all over. Now, if n is equal to 2, n is equal to 2 is the L shell, right? Now, the L values, which is the azimuthal quantum number, will go from 0 to n minus 1. So 0 to n minus 1 will be, let me clean this space and use it. 0 to n minus 1 would be 2 minus 1, and that will be 1. So the L values will be 0 and 1. Now, the 0 will stand for S, and then the 1 will stand for P, right? Good. So, and then I told you these ones are accompanied with shapes. And so once you know we have S, you know it's spherical. If you know it's P, you know it's dumbbell shape, right? Now let's do the last example here. N is equal to 3. The L values will go from 0 to n minus 1, which will be 3 minus 1. And so we'll have 2. So the L values will be 0, 1, and 2. 0, 1, 2. Right? This will be S, this is P, and this will be D. Right? These are the symbols. And these symbols are from the behavior of these orbitals when we observe them. Right? The spectral lines produced by these orbitals. Right? This is simple. S is simple. P is principal. D is diffused. Right? And F is fundamental. So these are the interpretations of the symbols that we use to represent these azimuthal quantum number. Now, there's one thing about azimuthal quantum number that I've not said yet, that the azimuthal quantum number helps us to know the number of subshells. And so I said that the principal quantum number tells us the number of shells, right? Now, the azimuthal quantum number helps us to know the number of subshells. So for n is equal to 1, right? The L value is only 1, which is L is equal to 0. So there's one subshell. There's one subshell in the first energy level, which is the K. Now for n is equal to 2, right? The L values, that is from 0 to n minus 1, is 0 and then 1. That means there are 2 subshells in n is equal to 2. Now n is equal to 3, we have L values of 0, 1, 2. That means there are 3 subshells. These are very important, so we take note of them, right? Good. Now let's move forward with our discussion. So the d orbital is more complex. Yes. The next quantum number is the magnetic quantum number. The magnetic quantum number. Now, the magnetic quantum number tells us the orientation of orbitals in space, how orbitals are oriented in space, right? And then it takes values from negative L to positive L. So it takes integers from negative L to positive L, including 0. Very important, including 0. And so if we are taking it from up to down, from where we started from, we assume that when n is equal to, when we are talking about the first energy level, n is equal to 1, which is the K shell, right? Now the L values will move from 0 to n minus 1. N minus 1 here is 1 minus 1, which is 0. So the L values here will be 0, which stands for the S orbital, right? Now the ML values, right here, they have made the MI. Usually it's ML. That's how it's supposed to be, right? The ML value here would be from negative L to positive L. There's no negative or positive side of 0, so it's still 0. That means that the S orbital here has only one orientation, right? Yes, now from the azimuthal, realize that it's spherical. From here, we are seeing what? It has only one orientation. So we say it is non-directional. That is what has been put in yellow here. The S orbital is non-directional. Now let's do the same for n is equal to for n is equal to 2. Let me change the ink. N is equal to 2. Now the L values will take from 2 to n minus 1, which is 2 minus 1. That will give me 1. So the L values will be 0 and 1. That is for S and what? P. Now, if I look at the ML values, I take each of these independently. So the ML value for the S orbital is still 0. But the ML value for the P orbital, which is 1, will be -1, 0, and +1. Good. Now, this one will tell us that the S orbital has one orientation, hence it's non-directional. But then the P orbital has 3 different orientations. Can be oriented, we have 3 different orientations. It can be oriented on the x-axis, the y-axis, and the z-axis, right? So that is why we have these 3 values. So it shows us the number of orientations. Very important. Let me do for the last one. Let's take n is equal to 3. If n is equal to 3, then our L values will go from 0 to n minus 1. So 3 minus 1 is 2. So my L value will be 0, 1, and 2. 0 is S, 1 is P, and then 2 is D. My ML value, I will take each of these individually. So my ML value for S orbital will be 0, non-directional, 1. My ML value for P, right, will be -1, 0, and +1. Always ML value takes it from -L to +L, including 0, right? So it means this one has 3 different orientation. Now, the ML values for D will be -2, -1, 0, +1, +2. So I would have 5 different orientations, right? 5 different orientations of the D orbital. Very important to note. Now, one thing that hasn't been said that I want us to put on record is that the ML value, that is the magnetic quantum number, will tell us the number of orbitals in a subshell. The number of orbitals in a subshell. So the S orbital is non-directional. It means it has just 1 orbital, just 1. Now the P orbital, which has 3 orientation, will have 3 orbitals. So that the subshell, the P subshell, will have 3 orbitals like this. Now the D would have 5 different orbitals. 5. So 5 orbitals like this. And the 5 orbitals will show us the 5 different orientation in spaces that we have. Very important to note. Let's continue our discussion. There's one last quantum number that we have to consider. Yes. So I've explained all these. The F orbital will have 7 different orientations. It starts from -3 to +3. Very important to note. Very important to know. Now, the last type of quantum number we have is the spin quantum number. Now, the spin quantum number is showing us the direction of spin. We are saying that electrons are not static. Electrons, they rotate on their axis. Now, the rotation can either be clockwise or anti-clockwise. And the spin quantum number will show us the direction of spin of what? Of the electron. So it shows the orientation. These are the possible figures that we can have for spin quantum number, either negative half or positive half, right? Positive half showing clockwise rotation, negative half showing anti-clockwise rotation. So that will be that for that's right. So these are the 2 possible orientations of spin. These are the possible rotations, right? Direction of rotation of electrons. Now, the reason why we have to learn the quantum number so that we can describe electrons completely is to help us to draw the electronic configuration. Now, from what we have learned in DHS or SHS will be what we call the first one, that is electrons arranged in shell using only the principal quantum number. So if I'm supposed to draw, let's say sodium, right? Sodium atomic number 11. If it's in a neutral state, it means the number of electrons is also 11, right? And so if I'm drawing sodium like this is sodium, Na11. Now this is what I draw. I draw the nucleus, right? Then I draw only the principal quantum number. So shell 1, it takes 2 electrons, 1, 2. Then I'll draw another one. right? That is 2. It takes 8 electrons. Remember, the number of electrons that can enter is 2n squared, right? That's what we use to determine. So it takes 8. 1, 2, 3, 4, 5, 6, 7, 8. I've exhausted 10 electrons. There's one last electron that can happen. I draw another shell and then add the last electron. So that is what I look at. And this is the first one. This is basic. This level, we draw another type of configuration. That is the second approach. Electrons arranged in shells using all the 4 quantum numbers. And that is what we do. Before we can do that, we need 3 rules. These rules are guiding principles that will help us to write and draw our electronic configuration. The drawing that we will draw will be the orbital box diagram, and then we can also write the configuration using all the 4 quantum number. Now, the first in no particular order is the Aufbau. It's the Aufbau's rule or Aufbau's principle. Now, it states that electrons' energy levels must be filled starting from the lower energy level. Very simple. So we are saying that when you are filling the orbitals, right, fill them, start from the one with energy, lower energy level, before you go to the ones with the higher energy level. Now, we have to do that because the ones with lower energy level or the ones at lower energy level are more stable. That is the reason, stability. Now, when we are filling configurations, what we have to put in our head always is stability. Everything we do is stability, right? Everything we do is about stability. And so this rule is telling us that let's not forget about stability. Let's always fill the orbitals with lower energy before we fill the ones with higher energy because they are more stable. Very simple. Next one talks about Hans' rule of maximum multiplicity. Hans' rule. Now, Hans' rule introduced a technical term that we have to be careful of. The technical term is degenerate orbitals. Degenerate orbitals. So we have to ask ourselves what degenerate orbitals are. Degenerate orbitals. What are degenerate orbitals? Now, I told you, the s orbital is non-directional. It has only one suborbital. So it's like that. Right? It's like that. But then if you move and you go to the p orbital has the p subshell has 3 orbitals under them. The px, the py, and the pz. Right? Now, these orbitals have the same energy. And so we call them degenerate orbitals. From this, you can now define degenerate orbitals as orbitals of the same energy or orbitals having the same energy. Another example would be the d orbitals. I've already stated up there that the d orbitals and the d subshell has 5 different orbitals, right? Now, these orbitals have the same energy. We call them degenerate orbitals. Now, Hans' rule talks about how we can fill degenerate orbitals. He's saying that if we encounter degenerate orbitals like this, we have to fill them singly with electrons with parallel spin before we pair them up with electrons with opposite spin. It's a lot of English, but what we are saying is very simple. We are saying that if we are filling degenerate orbitals like the p, and then let's say I have 5 electrons that will go here. Now, I don't have to start filling it like this. Give this 1, 2, give this 1, 2, and then come and give this 1. No. What I have to do is that I have to draw this one anyways, and then give each of them, because they have the same, give each of them 1 with parallel spin. So like this, 1, 2, 3. And when I'm done, the excess, I'll come and then pair them up with opposite spin. The first 3 should be parallel spin. Before then, I come and then pair the next 2 with opposite spin like this. Right? If I'm filling the same, using the same 5 electrons to fill the D, because they are degenerates, I have to fill them singly. So instead of doing 2, 2, and 1, no, I won't do that. The 5, this is what I will do. The 5 orbitals, this is what I will do. I would have to fill each of them singly. 1, 2, 3, 4, 5. Before, if there is excess, I'll come and pair them up. So you realize that there's a difference here. Now, this is different from this. This is the right one. This is the right thing that we are supposed to do. And that is what Hans' rule of maximum multiplicity has told us. Now, if you have been following the conversation, you realize that in each orbital, I put just 2 electrons there. The electrons are these things that I put there, right? The half rotations that I put there, clockwise, anti-clockwise rotation, the half rotation that I put there. But what told me that it has to be 2? And that is when we go to the last principle called the Pauli's exclusion principle. Now, the Pauli's exclusion principle can be stated in different ways, right? The first way, which is not here, is the maximum an orbital can hold is 2. The maximum number of electrons an orbital can hold is 2, and they must always have opposite spin. That's one of the ways. That is why in each of the small box, I put 2 electrons there. That is because of the Pauli's exclusion principle. Now, in a very simple term, we are saying that no 2 electrons in an orbital will have exactly the same 4 quantum numbers. No, it can never happen. And so there's no way that you can get something like this. You can get something like this. This is p orbital. And then we have something like this. Up here, going, the 2 orbitals going up. When the 2 electrons here are going up, that means they will have the same 4 quantum numbers. They will have the same 4, and that is not possible. That is not possible. It's not possible because this one is against stability, because they are all rotating towards the same angle. The repulsion here is too much. Usually, you want them to rotate at opposite directions so that the repulsion, the rotation can cancel out, their effect can cancel out to increase stability. That is what we are looking at. That is what we look at. Very important. That is what we look at. Stability. So that's Pauli's exclusion principle. We can state it as it has been stated here that no 2 electrons in an orbital will have the same set of 4 quantum numbers, or we can state it as the maximum an orbital can take is 2 electrons and they must have opposite spins. Very important to note. Good. Let's move on. Moving on. Now, after learning all these 3 rules, we are well equipped. We are well equipped to now write configurations. Now, this is the first approach, very simple, 288, right? So first, a orbital will take 2. There's no differentiation here. We just use the main energy level. That's the first approach. Now, the second approach is when we apply all the 4 quantum numbers. Now, before, if you have followed the discussion about the 4 quantum numbers, let me share screen and try and explain everything that has occurred here to us. I'll try and explain everything all over in like less than 2 minutes. Let me share a white screen. All right. So this is our white screen. Let's talk about the quantum numbers all over again. Now, summary. N is equal to 1. When n is equal to 1, right? The L value will take from n 0 to n minus 1, which is 0. Now, the 0 is for s orbital, right? The ML value here would be 0 because 0 will not have positive or negative numbers, right? It's very simple. Now, the name of this subshell is 1s subshell. 1 coming from the main energy level, and then the s coming because of the 0 here, right? 1s. And then it will have only 1 orbital under it, 1, because there's only 1 number here, right? Only 1 orientation. Very simple. Now, if I'm looking at n is equal to 2, if I'm looking at n is equal to 2, now my L value will take from 0 to n minus 1. That's 0 and then 1, right? Now the 0 is S, it's represented by S. The 1 is represented by P, right? Good. Now, this subshell is called the 2s. 2 coming from the main energy level, and the s coming from this 0. And then this one, this p will become 2p. Now, if I'm looking at ML value, I told you we take them separately. So for the s here, the 0 will still be 0. There's no negative or positive. So the 2s will still have only one orbital under it, right? Now, the ML value for the p, for the p orbital, the ML value for the p orbital, I would have -1, 0, and +1. Remember, the ML value takes value from -L to +L, including 0. So 3. So I would have 3 like this. Let me do one last one. Let me go to n is equal to 3. Now, when n is equal to 3, my L values will be 0, 1, and 2. 0 is represented with S, 1 is P, and 2 is D. Now, if I add energy level as I'm supposed to, I would have 3S, 3P, and then 3D, right? So these are the energy levels, 3D. Good. Now, the ML value for S will still be 0. There's no positive or negative, so we'll have just one subshell. The ML value for P would be -1, 0, and +1. 3 different orientation, 3 subshells. So 3 orbitals, sorry. Then the ML value for D would be -2, -1, 0, +1, +2. So 5, right? So the D would be like this with 5 orbitals. That is it. Now, if I'm supposed to group this together, you realize that I have 1s in the first energy level. I have 2s, 2p in the second energy level. I have 3s, 3p, 3d in the third energy level. Then I have 4s, 4p, 4d, 4f. Now, for the purpose of our discussion, we can end here. When we are looking at how the energy level goes, because our vow told us that we have to fill the lowest energy level first. This is how it goes. This is the lowest, go like this. So I'm putting an arrow there so that I can do the arrangement. Now, you don't have to know how these arrows work, but you just have to know how to write them. This should be 5s. Now, if I'm writing the orbitals, I am arranging them in terms of their energy level. This is what I will have. The one with the lowest energy level that has to be filled first is 1s, followed by 2s. So like how the arrows are going, 1s, then it crosses 2s. Then it comes and crosses 2p. So it goes to 2p, then it goes to 3s, right? Then from 3s, I go through 3p, then I go through 4s, then I go through 3d, right? Good. Now, this is what we are supposed to note. This is the arrangement of the orbitals in order of increasing energy level. Now, the arrangement is very simple. It goes from 1 to 2 to 3. The only change is between the 4s and the 3d. The 4s and the 3d. Now, the 4s, even though it's on the 4th energy level, has a lower energy than the 3d. And so always when we are filling, in order to obey Abba's principle, we fill the 4s before the 3d. Let me repeat that. When you are filling, you fill the 4s before you fill the 3d. Very important to note. But then when we are writing, in most of our writings, right, we still write the 3d before the 4s. So if I'm writing this, if I'm writing a configuration, I'll write it like this. But then always remember that you have to fill the 4s before the 3d. Very important to note. Now, let me shock you again. When this atom is losing electron, this one is losing electron. The electron is lost from the outermost shell. And so even though 4s has lower energy And so we are filling it before the 3D. When it is about losing electron, it will lose from the 4s before it loses from the 3D. So the 4s still maintain its status as the outermost electron. As the outermost electron. I'll use an example to illustrate. Very important to note. But then when you are filling the electron, you always make sure the 4s is still before the 3D. Now let's go. I told you one of Pauli's principle, one of the ways of stating is that the maximum each orbital can take is 2. And so 1s has only one orbital, right? So the maximum electron that can go here are 2 electrons. Now 2s still s orbital, so it still takes 2 electrons. Now 2p, the p has 3 orbitals and the p subshell has 3 orbitals, right? And so it can take a maximum of 6 because each of them is taking 2, 2, 2, right? So it can take a maximum of 6 electrons. Now the 3s, the s orbital on the third energy level, is still 3s, right? So it will still take 2. It's still s, it will take 2. The 3p will take 6. And then the 3d has 5 orbitals, so it can take 10, up to 10 electrons. The 4s will still take 2 electrons. Let's attempt filling or drawing some electronic configuration. Now, let me give myself an example. Let me draw sodium. Let me draw scandium, 21. Yes. Let me draw scandium. Let me draw chromium, 24. Yes. I think these are okay. These are okay. Now, these ones are special. Let me add nitrogen. Nitrogen. These are special. Good. So now let's obey. These are neutral atoms. The 7 here are not the number of electrons. Even though electronic configuration shows arrangement of electrons, the numbers here are not numbers of electrons. They are numbers of what? Protons. They are called atomic number. But in the neutral atom, because the atom bears no charge, in the neutral atom, we know that the number of electrons is equal to the number of protons. Hence, we can say that in the nitrogen above, the number of electrons is 7, and we are right. Right? So let's write the electronic configuration. Now, I would have 1s, 1s2. I've taken 2 electrons out, it's left with 5 electrons. Then I have 2s2. I've taken 2 other electrons, so it's left with 3. Then 2p. 2p can take up to 6 electrons, right? But there are only 3 left, so I'll put the 3 there. If I am drawing the orbital box diagram, S has just 1 subshell, S has 1 subshell, the p has 3 orbitals. If I am filling as I should, this one will have 1, 2, 1, 2. Now, may God forgive anybody who wants to do this like this, 1, 2, 1. Because this one would be in disobedience to the Hans rule of maximum multiplicity, which states that degenerate orbitals have to be singly filled. And so because of Hans rule, this is wrong. We cannot do it like this. No, we can't do this. We have to first of all fill these with single parallel spin. So I have to fill it 1, 2, 3. Now this is a half-filled orbital. The half-filled orbital is stable, very stable. If I compare this to oxygen, oxygen is like this, O8, right? Now I have 1s2, 2s2, 2p4, right? If I'm drawing the orbital box, it's like this, 1, 2, 1, 2, and this is 1, 2, 3, 4, right? Because this is half filled, it is more stable. Always, in terms of stability, the fully filled shells are more stable, followed by the half filled before partially filled. So this is partially filled. This one is partially filled. It is not half, it is not full, it is partial. But this is half filled. And half filled is always more stable than what? Than the partially filled. But fully filled is also more stable than what? The half filled. So these are very, very simple principles that we have to keep. Now let's quickly run to nitrogen. Nitrogen has 11 electrons in the neutral state. So I have 1s2, 2s2, 2p6, right? It will still be left with 1 electron. So 3s1. If I am drawing the electronic, the orbital box diagram, So this is 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6. Very important. Let me draw this well. Yes. And then this is 1. Right? This is how we draw it. Now, scandium, transition metal. Scandium is a transition metal. Let's do for scandium. So scandium would be 1s2, 2s2, 2p6. I've used 10 electrons. Let's go. There are 11 more. 3s2, 3p6. Now I've used 18 electrons. Let's go. 18 electrons. Let's go. Then I have 3d and I have 4s. Always remember to fill the 4s before the 3d. I've used 18, it's left with 3. I'll come and fill this one with 2 electrons, right? And then the last electron will go to the d. The last electron will go to the d. The last electron will go to the d. So this is how we fill this. If I'm drawing the orbital box diagram, this is like this: 1, 2, the s orbital here, 1, 2, the p orbital, 3 orbitals under this sharp shell. We have 1, 2, 3, 4, 5, 6. And this is 1, 2, 1, 2, 3, 4, 5, 6. Then the d orbital has 5 subshells. Right? Good. So it has just 1. So 1 will be here. Then the 4s. Remember, I filled my 4s before my 3d. I filled my 4s before my 3d. That is the trick. That is the trick here. Very important to note. Now let me do chromium. Chromium comes with a special condition. It's not the only thing, right? Chromium comes with a special condition. So I have to draw it to show as a special condition. 1s2, 2s2, 2p6. I've used how many? 10. 3s2, 3p6, right? I've used 18. Now write 3d, I will not fill it. Then I'll come and write 4s, 4s2. So now I've used 20, right? So the last 4 will go here. Very important. If I'm drawing the orbital box, this is 2 electrons. This will be 2 electrons, 6 electrons here. 1, 2, 3, 4, 5, 6. Notice how I fill them singly because of Hans' rule of maximum multiplicity. 1, 2, the p orbital. 1, 2, 3, 4, 5, 6. Very important. Now the d orbital has 5 suborbitals, so we can look at this is 1, 2, 3, 4, right? The 4s here will be 1, 2. That is it. Now, this is how it was supposed to be ideally, but this is wrong. This is wrong because of what I have talked about, that half-filled orbitals are more stable than partially filled. What we have done here is a partially filled D, and it's not stable. And so what we can do is that because always arrangement or configuration, we have to arrange them to assume the most stable state. It is compulsory. It is compulsory for us to arrange the electrons for the atom to assume its most stable form. And so this is what we will do. Yes, and these are exceptions for just 2. I'll tell you the other one. The atom number 29 has this exception too. It has this exception. So we would move 1 from here. So we'll move 1 from here. Move 1 of the electrons from the 4s. Move 1 of the electrons from the 4s. 1 of the electrons from the 4s. So this place will be left with 1. And this one, I'll write 1 here. Then I'll bring it here so that this place becomes 5. And I'll bring it here. Now, when I do this change, this one becomes half filled. This one becomes half filled. And always half filled is more stable than what? Than partially filled. And so because of the half-filled nature of this one, this is more stable, and hence this is the preferred representation of chromium. This is the preferred representation of chromium. Very important to note. This is the preferred representation of chromium. Good. Now let me explain two important concepts and we'll go back to the slides. Let me explain two important concepts. Concept one is that I told you that when we are removing electrons from, let's say, chromium, even though we fill the 4s before we fill the 3d, but we'll come and remove the electrons from the 4s first. So let's say it's losing one electron to become Cr plus. We will just take this electron off. So this one will become 4s0. Right? Good. Because the 4s still maintain its integrity as the outermost shell. But because of Abao, because it has lower energy, it has to be filled before the 3d, which has higher energy. The next thing is that when we are filling such a configuration, we can start from somewhere. Instead of starting from 1s every time, we can start from somewhere. So I have something, if I have something like neon is number 10, right? Neon is 1s2, 2s2, 2p6. Now, if I want to draw the configuration for something like, let's say, sodium, like I have drawn here, I can decide not to start from the basics, start from all of these places, because all of this is for neon. So I can just do something like this, into square brackets, neon, and then I'll come and add 3s1. So this one shows that I am doing everything for neon and I'm adding what is in addition. Let me repeat that same thing with a different example. Let me narrate that with a different example. Now, argon is 18, right? The configuration for argon is 1s2, 2s2, 2p6. Now I've used 10 of them. 3s2, 3p6. This is fully filled. This is argon and inert gas. Now, if I want to draw scandium, instead of starting all the way from scratch, this is how I can draw scandium. This is how I can draw scandium. Let me clean up here so that I can put scandium there. Now, this is the first configuration of scandium, which is still correct here, right? But if I don't want to stress, I can take all of this up to this point as for argon. So I can just say SC21. Then I'll do into square brackets AR, that is argon. Then I'll do 3D1, 4S2. I'm done. For chromium, this is what I can do. I can take argon, which will take up 18 of the electron. Then I'll write my 3D and then the 4S. So 3D5, 4S1. I'm done. So this is another way of representing, which we will see in the slide. Let's quickly run back to the slide and then finish our conversation on the quantum numbers. So what we have been shown here are yes, so these are examples of configuration. I've explained all of them. These are the order. This is the order of the orbitals in terms of energy, increasing energy level. Now, the slide said we should learn the first 30 elements, and the first 30 will always end in 3D. That is why I stopped here. But if we continue, we get the 4P, the 5S, 4D, so it continues like that, right? Now, look at how they have written the transition element. Titanium, they started from argon and just added the next piece, right? When it gets to chromium, instead of getting the 4S2, we have 4S1 because of what? Because half-filled is more stable, right? Because half-filled is more stable. And the same thing is for copper. Copper is 29. Ideally, this one is supposed to be 4S2, then 3D9. But the truth is, if we take one electron from the 4S2 and add, this becomes fully filled. And fully filled is more stable than half-filled and more stable than partially filled. So that's what we'll do. We take one electron from here and add here. So we have to take note of this. This is different from the normal order, right? That is that for that. Now, our next conversation will be around the periodic table and the periodic property. This periodic table, as used now, is developed by Mendeleev, Dmitry Mendeleev, who is a Russian. Right now, Mendeleev developed this or arranged these elements based on their atomic masses. But then after that, we have now discovered the atomic numbers. And so that is what we have used to refine our current periodic table. So our current periodic table, the arrangement is so as Mendeleev did, but then now we use the atomic numbers, right? Yes, and it's a widely accepted way of arranging because it helps increase the predictability of the properties, the periodic properties of elements in the periodic table. Now, because of this arrangement and how the properties vary with the atomic number, we have formed something that we call the periodic law. So let me state the periodic law before I move on. The periodic law. Now, the periodic law is very simple law that just tells us that the periodic properties, whether the physical or chemical properties of elements, are as a periodic functions of their atomic numbers. What accounts for the physical and chemical property of elements are their atomic numbers. So the periodic law states that the periodic property of elements are a periodic function of their atomic numbers. That is it. Now, in the periodic table, we have divided them into groups and then periods, right? So has been divided into groups and periods. Yeah, so groups. Now, groups will be the vertical arrangement of elements. Vertical arrangement of elements. Elements in the group have the same valence electron or similar electronic configuration, right? So, if you are in the same group, if you are in the same group, it means you have the same number of valence electrons. So, if you are in group 1, it means you have 1 valence electron. Group 2 has group 2 valence electrons, right? Group 3 has 3 valence electrons. That's very simple, right? Good. Now, we are saying that similarly, atomic configuration has only 1 electron outside a noble gas configuration. In most elements, the number of valence electron is the same as the group number, right? So very simple. Where the group members share similar physical and chemical properties, we call them a family. So we have examples of families like alkali metals. The alkali metals are group 1 element. They have similar properties. We have the halogens, which are group 7 elements, except astatine. Astatine doesn't share a common property as the other group 7 elements. Then we have some which are isolated. Some are isolated. Like group 4. Group 4 is not a family. It has carbon and silicon. Elements in the same group have different atomic numbers. So the different, it has different n numbers. The n numbers will be the principal quantum number. And so if you look at this, there's a very typical example. And we have LINAK and this rubidium and cesium, right? Now, these are all in group 1. They are all in group 1. But the n value for this one, right? The n value for this one is 2. The highest n value is 2. This is 3. This is 4. And so it goes like that. 5, 6. It goes like that, right? That's 4. What is that for that? So if you are in the same element, it doesn't mean you have the same principal quantum number. Your n value differs. Good. Next up, the periods of the periodic table. Now, period will signify the horizontal arrangement, right? If you are in the same period, it means you have the same main energy level, the same main energy level of the valence. So the valence electron would have the same energy level. So all the elements in period 1, their valence electron is in the energy level 1. Energy level 1. If I'm supposed to explain, let me draw this configuration there. Period 1 has only hydrogen and helium. So hydrogen and helium is, hydrogen is 1, right? It's 1s, 1s1. Helium is 2. So we have 1s2, right? Now, the valence electrons are these ones, right? The last electron, they are here. They are all in energy level 1, so they will be in period 1. And they are only the two elements in period 1. It doesn't go beyond that. Now, if you look at elements in period 2, like lithium, right? Lithium would have a configuration of 1s2, 2s1. right? Now, because the valence electron is the last electron, because the valence electron is in energy level 2, right? It will be in period 2. So the period you are in will show the energy level, the main energy level that your valence electron is in, right? Good. So that is it. We have some facts here that we can take note of. They are not things that for us to even chew. Very simple facts that we can appreciate. Period 1 has only 2 elements. Period 2 has 8 elements. Period 3 has 8 elements. Period 4 has 18. Period 5 has 18. Period 6 has 32. 32. Now, if you want to predict them, very simple. If you take period 3, the S can take 2 electrons. The P can take 6 electrons, right? If you add them, you get 8. So they had 8 different elements that can enter there. This is the S here. The 4S can take 2. The 3D can take 10. The P here can take 6. If you add them, you get 18. That's why we have the 18 here. So very simple, right? Very simple. Now, they are also showing you that these blocks would happen in this period. So if you take period 6, the elements you see in period 6, they enter the S, F, the D, and then the P. These are the orbitals which their valence electron fill. Very simple concept for us to keep notes. I mean, we don't have to chew these ones. Now, they are saying that for clumsy arrangements, the elements with their valence electron filling the 4s are placed in separate rows at the bottom of the periodic table. The row forms the lanthanides. Now, the 4f elements that go into the 4f, because we don't want the configuration to be very congested, because now the f orbital alone can take 14 electrons. So 14 elements. If we decide to put them there, it will make the whole arrangement cumbersome. So we have separated them. So if you check your periodic table, you see that we separated the F block, right? Now the 4F, the element that goes into the 4F orbital, we call them the lanthanides. The lanthanides, right? And then elements that go into the 5F, which is just under the 4F, right? We call them the actinides. The actinides, right? So that's for this one. The 5F is actinides, the 4F is the lanthanides. Now they start from thorium to lawrencium. Very simple. Now, one way of considering the periodic table is in the group of periods, but that's not the only way. We have another way of classifying the periodic table. We call them the blocks. The blocks. Now, the blocks are the orbitals. And so the blocks, we have the S block, which is S orbital. We have the P block for the P orbital. We have the D block for the D orbital. We have the F block for the F orbital, right? Now, the rationale is that if you have your valence electron entering the S orbital, you are in the S block. If you have your valence electron entering the P block, you are in the P block, right? Entering the P orbital, you are in the P block. If you have your valence electron entering, say, the F orbital, then you are in the F block. So that's how we use the blocks to categorize. So we are saying a group of elements with their valence electron occupying the same orbital. Valence electron in the S orbital in group 1 and group 2. So group 1 and group 2 combined is called the S block, right? S block. Group 3 to group O, right? Combined is called the P block. Now they form the main groups, the main group elements of the periodic table. Now the D block would form the transition elements, right? Now they start from the fourth period, right? So the fourth period, you have elements ranging from scandium to zinc, 21 to 30, right? That will be the first series. Then we have yttrium to cadmium, That's on the fifth period. Then we have lanthanum to mercury. That will give you the third series, right, on the period. So the truth is, lanthanum in itself is not a transition metal. It is in block F, right? So lanthanum Lanthanum is sometimes separated and then added to the lanthanide. So it's the starting element for the lanthanides, right? Because technically it is an F block, not a D block. It is an F block, not a D block. So we have to take note of that, right? The F block elements are the lanthanides and the actinides. The lanthanides fill in the 4F, and then the actinides fill in what? The 5F. Now, I've already said this, that the S and the P block are the main group elements. Good. So this is where we'll end our conversation about quantum numbers and electronic configuration. Now, the next video, which will be part 3, will capture conversation around periodic properties, right? So we'll talk about the atomic size, the ionic size, the electron affinity, the electronegativity, and everything, right? That is what we'll capture in our next discussion. Thank you very much. And if you have any question, kindly see any member of the HESA academic.